In this lecture, we will study the energy and power contained in a wave. We need to know the power available in a wave to evaluate wave energy conversion devices. A wave has both kinetic and potential energy. Let's start with kinetic energy. Consider a differential element, the blue element shown here, which has the dimensions dx and dz. The element is moving in the x direction with velocity u, and in the z direction with velocity w. We can calculate the kinetic energy, which we know to be 1/2 rho v squared. So we have here, that's per unit mass, so we then multiply by mass, which is density times volume. So here we have the resolved velocity term, so squared u squared plus w squared. We have our dimensions dx and dz, and the third dimension dy is in the plane of the into the plane of the slide, and that is per unit wave crest length. So this common way of specifying wave characteristics. So if we integrate this, so we integrate over x from 0 to lambda, and also then over z from depth to the surface, mean surface height, and in this integration limit, in putting 0 here, we're assuming that it's a small wave amplitude wave assumption. So the height above of the wave above the mean height is small in comparison to the depth. So leaving out all the details here, I just want to get you some idea of how this is calculated. We find that the kinetic energy, if we integrate, we get the kinetic energy as rho g times the wave height squared times the wavelength lambda divided by 16. We can find the potential energy of the wave in a similar fashion. We essentially consider a differential element and find the potential energy of that element. And so that's simply the acceleration of gravity g times a height times the mass. And so in this case, the height is the height of the center of gravity of the differential element here, which has a width dx, and the height of that center of gravity is simply the depth of the water plus the wave position relative to the mean water height, and so d plus 8 over 2. The element of mass is the density times its volume, so our length is here d plus eta times dx in this dimension. And again, the third dimension is into the plane of the slide, so that's per unit wave crest length. So we can take this differential potential energy then, and we can integrate it. And in order to find how much is associated with the wave itself, we integrate first for the total system, the wave plus the water beneath it. So everything under the wave, here under the blue line of the wave, and then we subtract off the potential energy of the mean water height. So the rectangle contained here, which then is the second term. And if you do that, you get a formula which is exactly the same as the term for the kinetic energy, rho g h squared times lambda divided by 16. So the kinetic and potential energy terms are exactly equal. The magnitude of those two terms are equal. So the total energy contained in the wave then is the sum of the kinetic and potential energy, and again we're calculating that per unit wave crest length, so per unit wave into the plane of the slide. So the sum of the kinetic and potential energy then is E, which is rho g h squared lambda divided by 8. All right, now a useful parameter sometimes is what's called the energy density or specific energy, and it's the energy per unit area of wave. And so the dimensions of the wave, we have the lambda, which is the wavelength, and we also have the dimension into the plane of the board, the wave crest length, which will assign a unit value of 1. And so the energy density or specific energy is 8 times g times h squared divided by 8. Now, we want to know what power is contained in the wave, because any wave energy conversion device we study will be looking at how much of the power available in the wave can actually be extracted. So power is essentially the energy per unit time transmitted in the direction of wave propagation. Now, it's this wave propagation that creates some complication. We need to know the details of the wave spectrum. We need its wave propagation, velocity, and so forth. We can get around that to create a very simple formula by introducing the energy period, T sub E. So it's a period based on the energy content, which contains details of the wave spectrum. All right, the details of that are beyond the scope of the course right now, but we can, if we introduce this energy period, we can simplify our formula greatly. So the power per unit wave crest length then is just simply rho g squared h sub s squared times T sub E, the energy period, divided by 64 pi. So the two wave parameters we need then are the significant wave height and the energy period. So we'll talk about that in the next lecture. So let's put some numbers into this equation. So if I substitute some known values, especially the density of seawater here, and some unit conversions, we end up with the equation here. Power in kilowatts per meter of crest length is 0.491 times h sub s squared times the energy period. For the units are shown here for h sub s in meters and t sub e in seconds. This formula is often simply rounded to 0.5 and written in a very simple fashion here. Power is simply h sub s squared times t sub e divided by 2, right? So a very useful formula. So let's summarize what we've learned about energy and power contained in a wave. So we know a wave has both kinetic and potential energy, and the sum of those two are actually equal in magnitude. We can find the wave energy density or specific energy very simply, just knowing the wave height. And by knowing the significant wave height and the energy period, we can calculate the power per unit wave crest length. So h sub s squared t sub e divided by 2. So please try the practice questions that follow to become familiar with using these equations.